Hello students, in today's lecture we are going to learn kinetic theory of gases from NCERT section 12.7. We will also solve example 12.8 and 12.9. This is our disclaimer. By the end of this lecture you will be able to define and calculate the mean free path of gas molecules using kinetic theory of gases and understand its relationship with pressure, temperature, and molecular size. In today's lecture, we will cover three main things. First, example 12.8. Then 12.7 mean free path. And last, example 12.9. Alright. So, example 12.8. A cylinder of fixed capacity 44.8 liters contains helium gas at standard temperature and pressure. What is the amount of heat needed to raise the temperature of the gas in the cylinder by 15 degrees Celsius? R equal to 8.31 joule per mole per Kelvin. So here we have to calculate heat Q. Alright. So let's now solve example. We will start to solving this example by using the given terms. So let's see. Volume V equal to 44.8 liters. So here we need to convert volume from liters to cubic meters. Remember, 1 liter is equal to 0.001 cubic meters. So we will multiply 44.8 by 10 raised to the power minus 3 meter cube. Alright. Temperature change delta T is equal to 15 degrees Celsius. So since the temperature changes are in same in Celsius and Kelvin, we can directly use 15 Kelvin for our calculations. This change will help us determine the heat needed. We also have the gas constant R, which is 8.31 joule per mole per Kelvin. Now let's consider the initial conditions. The problem states that the gas is at standard temperature and pressure, or we can say STP, standard temperature pressure. This means we have specific values for temperature and pressure. So temperature T equal to 273 Kelvin. This is the standard reference temperature for gases. Pressure at STP is 1.01 into 10 raised to the power 5 Pascal. This standard pressure allows us to use the ideal gas law effectively. The gas in question is helium, which is a monoatomic gas. This means it has specific heat capacities that differ from diatomic gases. For helium, the molar heat capacity at constant volume Cv equal to 3/2 R. This value is derived from the degrees of freedom of the gas particles. Alright. Now, to solve this, we will use the ideal gas law. This law relates pressure, volume, and temperature of a gas with the number of moles and the gas constant. So PV equal to mu RT, the ideal gas law. Here P is pressure, V is volume, mu is the number of moles. R is the gas constant and T is the temperature. This equation will help us determine the number of moles of helium in the cylinder. At standard temperature and pressure, 1 mole of an ideal gas occupies 22.4 liters. This is known as the molar volume. It's a useful concept because it allows us to calculate the number of moles in a given volume of gas under these conditions. So this universal volume is called molar volume. Means we can say cylinder's volume of 44.8 liters, it contains 2 moles of helium. This is because 44.8 liters divided by the molar volume of 22.4 liters per mole equals 2 moles. Since helium is a monatomic gas, its molar specific heat at constant volume Cv is 3/2R. It tells us how much heat is needed to raise the temperature of 1 mole of helium by 1 degree or 1 Kelvin. Alright. Molar specific heat at constant pressure denoted as Cp. For helium, which is a monatomic gas, Cp is calculated as 3/2R plus R. So when we add both terms, you will get 5/2R. This formula accounts for the translational and rotational degrees of freedom of the gas molecules. Since the volume of cylinder is fixed, we need to consider the molar specific heat at constant volume Cv instead of Cp. So this is because the heat required is determined by the conditions under which the gas is heated, and in this case the volume remains constant. Therefore, heat required, we can calculate, we can say heat required is equal to number of moles into molar specific heat rise in temperature. So substitute the values. We have heat required is equal to 2 moles into 1.5 R into 115. This simplifies to 45 R. Here we used 2 moles because the problem implies a standard molar volume, and 1.5 R is the specific heat at constant volume for helium. So when we solving, you will get heat required equal to 45 R. Now now we substitute the value of R into our equation. So heat required is equal to 45 into R, and the value of R is 8.31. So just multiply, alright, and you will get the answer. This step involves multiplying the calculated value by the gas constant to find the heat in joules. So solving this, you will get heat required is equal to 374 joule. This is the amount of energy needed to raise the temperature of helium gas in the cylinder by 15 degrees Celsius. Alright. Now we are focusing on the concept of mean free path and molecular collisions. Here we will understand mean free path and molecular collision relationship fundamentally. So let's start by considering the motion of gas molecules. As we know, in a gaseous system, molecules don't move in a straight line without interruptions. This figure illustrates the erratic motion of gas molecules. Gas molecules move randomly. Notice how they constantly change direction. This is a key characteristic of gases that we will explore further. So here molecules move randomly, or we can say in zigzag motion. The directions of the molecules are not fixed. The reason for this random motion is the molecules collide with each other. These collisions cause changes in their speed and direction. It's important to understand that these collisions are frequent and random, which affects how gases behave. Between each collision, a molecule travels a certain distance, which we refer to as the path length. This concept is important because it helps us quantify the behavior of molecules in a gas. Keep in mind that this path length varies with each collision. Now, path length here is mean free path. So let's define the mean free path. This is the average distance a molecules travel between collisions. It's a fundamental concept in understanding gas behavior, as it provides insight into how often molecules collide. Symbol for mean free path is L. This notation will be used in equations and discussions about molecular motion. So let's see. Mathematically, mean free path can be represented as follows. L equal to 1 upon under root 2 n pi d square. Here L represents the mean free path. This equation is central to our understanding of molecular motion in gases. So it's important to grasp each component. Where in this equation, d stands for the diameter of the molecule. N in the equation represents the number of molecules per unit volume. A higher density of molecules means more frequent collisions, thus a shorter mean free path. Alright? Understand derivation of mean free path. So consider gas molecules as spheres of diameter d. Look at the figure. Look at here. Which illustrates the motion of gas molecules. They move and interact within the space. So here we will focus on a single molecule moving with an average speed represented by the symbol b bar. This average speed is an important factor here to calculating the mean free path, as it influences how frequently a molecule will encounter other. Keep in mind that this speed is an average, considering the random motion of all molecules in the gas. Here, collision occurs when the centers of two molecules come within a distance equals to the diameter d. This concept is fundamental because it defines the conditions under which molecules interact, allowing us to calculate the mean free path. Alright? So this is the sphere and their diameter is d. So in a given time interval delta t, the molecule sweeps out of volume. This volume is represented by the formula that is pi d square v bar delta t, where d is the diameter of the molecule and v bar is the average speed. Alright, this visual representation helps us understand the space a molecule covers as it moves. Now, within this swept volume, we can determine the number of point molecules present. This is important because it tells us how many potential collisions our molecule might encounter. Understanding this helps us quantify interactions at the molecular level. So the number of collisions that occur in the time interval delta t can be calculated using the formula n pi d square v bar delta t. Here n represents the number of molecules per unit volume. This equation is fundamental as it links the physical movement of molecules to the probability of collisions. N is the number of molecules per unit volume. This is a key factor in determining how often collisions occur, as a higher concentration means more frequent interactions. From this, we can derive the rate of collisions for a single molecule, which is given by n pi d square v bar. This rate is a measure of how often a molecule will collide with others, providing insight into the dynamics of gas molecules. Average time between collisions, denoted as tau. This is calculated as tau equal to 1 upon n pi v bar d square. Understanding tau is important as it gives a measure of the mean free path, or the average distance a molecule travels between collisions. Alright. Now, mean free path are denoted as L. It is the average distance between successive collisions of a gas molecule. So, notice the figure illustrating the gas motion of gas molecules, which helps visualize this concept. The term successive collisions, as it highlights the continuous movement and interaction of molecules. Now, let's look at a mathematical expression for the mean free path. It's given by the formula that is L equal to V bar tau, which is equal to 1 upon n pi d square. Here n is the number density of molecules and d is diameter of molecule and pi is a constant. This equation 12.39 is important as it links the mean free path to the physical properties of gas. So by considering the relative motion of molecules, we refine the mean free path formula to L equal to 1 upon root 2 n pi d square. This adjustment accounts for the fact that molecules are moving in different directions, which affects the frequency of collisions. This refined formula is more accurate representation of molecular interaction in a gas. So let's start by estimating the mean free path, denoted as L, and time between collisions tau for air molecules. We know that at standard temperature and pressure STP, the average speed of air molecules is approximately 485 meters per second. This speed is an important factor in determining how often molecules collide. Alright. Next, we need to consider the number density of the molecules, which is the number of molecules per unit volume. At standard temperature and pressure, the number density N is calculated as 2.7 into 10 raised to the power 25 meter per meter cube. This high density indicates that the molecules are closely packed, leading to frequent collisions. The molecular diameter D is another important factor here in our calculations. For air molecules, the diameter is about 2 times 10 raised to the power minus 10 meters. Alright, and the size of molecules affect how often they collide, as larger molecule will have a high chance of interacting with each other. So time collisions, denoted as tau for air molecules at standard temperature pressure. This time is approximately 6.1 into 10 raised to the power minus 10 second. This short time interval reflects the rapid movement and frequent collisions of molecules in a gas. With these parameters in mind, we can now calculate the mean free path L. This is the average distance a molecule travels before colliding with another molecule. So L equal to 1 upon root 2 n pi d square. Here n is the number density, pi is the mathematical constant, d is the molecular diameter. This equation shows how to mean free path is inversely related to the number density and the square of the molecular diameter. So substituting the values into the formula, we have 1 upon root 2 into 2.7 into 10 raised to the power 25 into 2 into 10 raised to the power minus 10 into 3.143 into 2 into 10 raised to the power minus 10. This step involves plugging in the values for number density, molecular diameter and pi to calculate the mean free path. So solving this, you will be get L equal to 2.9 into 10 raised to the power minus 7 meters. And this value is approximately is around 1500 D. Alright, or we can say which is about of 1500 times the molecular diameter. This is clear? So factors affecting mean free path. The first factor is density. Alright, higher density means more molecules are packed together, leading to more frequent collisions and a shorter mean free path. And the next factor is molecular size. Larger molecules have a greater chance of colliding, resulting in a shorter mean free path. Alright, so these two important factors. These are two important factors. Example 12.9. Estimate the mean free path for a water molecule in water vapor at 373 Kelvin. Use information from exercise 12.1 and equation 12.41. Here we have to find out the mean free path for a water molecule in water vapors by using the information of exercise 12.1 and equation 12.41. So let's see the solution. So let's start with what we know. The temperature is given as 373 Kelvin. From exercise 12.1, this exercise provides us with essential parameters needed for our calculation. So from exercise 12.1, we have the molecular diameter of water denoted as D. Pressure P at boiling point is 373 Kelvin. Pressure, boiling point is 373 Kelvin. Mean free path. So we are trying to find mean free path. This is the average distance a molecule travels before colliding with another molecule. So L equal to 1 upon root 2 n pi d square. This equation shows how many mean free path depends on number density of molecules and molecular diameter d, where L represents mean free path, where d is the diameter of molecule. This is a measure of the size of molecule and affects how often collision occur. D is the diameter of molecule. All right. So the D for water vapor is same as that of air. This is an important assumption that simplifies our calculations, as it follows us to use known values for air in our equation. So number density, which is inversely proportional to the absolute temperature. This means that as the temperature increases, the number density decreases. So n equal to 2.7 into 10 raised to the power 25 into 273 divided by 373. This step involves simple arithmetic to adjust the number density from standard temperature to our given temperature. So solving this, you will get n equal to 2 into 10 raised to the power 25 per meter cube. This value will be used in further calculations to determine mean free path. All right. So hence mean free path L equal to 1 upon root 2 pi d square n. So substituting the values, we have L equal to 1 upon root 2 pi into 2 into 10 raised to the power minus 10 whole square into 2.7 into 10 raised to the power 25. So we plug in the diameter and number density directly into the formula. This substitution is important for calculating mean free path. So before we proceed with calculations, let's focus on calculating d square. This step simplifies our equation and ensures accuracy in our final results. It's important to handle these calculations carefully to avoid errors. So d square is equal to 2 into 10 raised to the power minus 10 whole square, which is equal to 4 into 10 raised to the power minus 20 meter square. This squared diameter is a key component in our formula, affecting the mean free path significantly. All right. So now substituting d square into the formula, we get L equal to 1 upon root 2 into pi into 4 into 10 raised to the power minus 20 into 2.7 into 10 raised to the power 25. Here we are using the molecular diameter and the number density of molecules to find the mean free path. So now substituting the values in the mean free path formula. So you will get this term. So L equal to 2.08 into 10 raised to the power minus 7. This value tells us the average distance a water molecule travel in a vapor before colliding with another molecule. All right. Now here is the summary of what we studied. Gas molecules move in irregular path due to contact collision with other molecules. Mean free path denoted as L. This is the average distance a molecule travels between successive collisions. Here L equal to 1 upon root 2 and pi d square. In this equation, n represents the number density, which is the number of molecules per unit volume, and d is the molecular diameter. When molecules come within a diameter d of each other's centers, a collision occurs. Volume swept by the molecule in a given time, denoted as delta t. The formula pi d square b bar delta t represents this volume, where b bar is the average speed of the molecules. The formula n pi d square v bar represents the rate at which molecules collide. Here n is the number density of molecules, d is the molecular diameter, and v bar is the average speed of molecules. The average time between collisions, denoted as tau, is given by 1 upon n pi v bar d square. For typical gases, mean free path is about 1500 times the molecular diameter. The large ratio indicates that molecules travel quite a distance relative to their size before colliding with another molecule. As we increase the density of gas or the size of molecules, the mean free path decreases. The time between collisions is typically around 10 raised to the minus 10 seconds. This is incredibly short time frame and highlights how rapidly molecules in a gas are moving and interacting with each other. Molecules travel with collisions with around 485 meters per second. This speed is quite significant and illustrates the high energy and rapid movement of molecules in a gas. Now, we have some practice questions. These will help you to build your concepts and improving your question solving skills, and most importantly, solving these questions will help you a lot of your exam preparation. So first question: a gas has molecules of diameter 2 into 10 raised to the power minus 10 meter and number density 3 into 10 raised to the power 25 molecules per meter cube. Calculate its mean free path. If the density of a gas is doubled while keeping temperature constant, what happens to its mean free path? The mean free path of a gas is 3 into 10 raised to the power minus 7 meter. If the molecular diameter is doubled, what will be the new mean free path? For a given gas, if number density n equal to 2 into 10 raised to the power 25 per meter cube and molecular diameter d equal to 3 into 10 raised to the power minus 10 meter, find the mean free path. The mean free path of a gas molecule is inversely proportional to on what factor? So these are the practice questions and this is homework for you. Thank you for your attention. See you in next class. Thank you.